Data engineering concepts. ETL versus ELT and data processing. 1. Data extraction. Both ETL and ELT start with extracting data from various sources. 2. Data storage. In ETL, data is first transformed then loaded into the data warehouse. In ELT, data is loaded into the data warehouse before transformation. 3. Data transformation. ETL transforms data before loading, ideal for structured data and established schemas. ELT transforms data within the data warehouse, more flexible for unstructured data and evolving schemas. Advantages and considerations. 1. Performance. ETL can be less resource intensive as transformation occurs before loading. ELT can leverage cloud data warehouse capabilities for powerful transformations. 2. Scalability. ETL might require more planning for scaling. ELT scales easily with cloud-based data warehouses. 3. Flexibility. ETL suits well-defined data schemas and stable sources. ELT offers more flexibility for changing data types and sources. Comparing ETL and ELT. 1. Process steps. ETL, extract, transform, load. ELT, extract, load, transform. 2. Data transformation. ETL transforms data before loading into the warehouse. ELT transforms data after it is loaded into the warehouse. 3. Data storage. In ETL, data is stored after transformation. In ELT, data is stored before transformation. 4. Performance. ETL can be less resource intensive upfront. ELT may require more powerful warehouse capabilities. 5. Scalability. ETL requires more planning for scaling. ELT is more scalable, especially with cloud data warehouses. 6. Flexibility. ETL is less flexible, better for stable schemas. ELT is more flexible, accommodating evolving data structures. 7. Suitability. ETL is suitable for structured, consistent data. ELT is better for unstructured, changing data sources. Similarities. 1. Data extraction. ETL and ELT both begin by extracting data from a variety of sources, which could include databases, CRM systems, spreadsheets, or other data stores. 2. Data integration. They both integrate data from these multiple sources. Integration involves combining data from different formats or making it consistent and unified, which is crucial for subsequent analysis. 3. Data processing. Both ETL and ELT processes involve handling large volumes of data. This stage includes sorting, aggregating, and transforming data into a format suitable for analysis or reporting. 4. End goal. The final goal of both ETL and ELT is to prepare data for analysis and reporting. This preparation enables businesses to perform analytics, generate insights, and make data-driven decisions. Differences between ETL and ELT. 1. Transformation. ETL, transformation occurs before loading data into the data warehouse. ELT, transformation takes place after data is loaded into the data warehouse. 2. Data storage. ETL, stores transformed data. ELT, stores raw data initially. 3. Performance. ETL, generally, less resource intensive upfront. ELT, requires powerful data warehouse capabilities due to the processing of raw data. 4. Scalability. ETL, scaling requires more planning and resources. ELT, easier to scale, particularly with cloud-based data warehouses that offer on-demand resources. 5. Flexibility. ETL, better suited for stable, structured data schemas. ELT, more flexible, accommodating evolving data structures and types. 6. Suitability. ETL, ideal for scenarios with structured, consistent data. ELT, preferred for unstructured or frequently changing data sources. Data serialization formats. 1. JSON, JavaScript Object Notation, a lightweight, text-based format, easy for humans to read/write, and for machines to parse/generate. Common in APIs and web services. 2. XML, extensible markup language, a verbose format, allowing complex data structures. Widely used in enterprise settings. 3. CSV, comma-separated values, simple format for tabular data. Each line represents a row, and fields in a row are comma-separated. 4. Avro, a binary format developed within Apache Hadoop. Focuses on compactness, schema evolution, and complex data structures. 5. Parquet, columnar storage format optimized for complex nested data structures. Common in data warehousing solutions like Hadoop and Spark. 6. Protocol buffers, protobuf, Google's language-neutral, platform-neutral format for serializing structured data. Known for efficiency and performance. 7. YAML, YAML markup language, human-readable format, often used for configuration files and data exchange where readability is paramount. 8. ORC, optimized row columnar, a highly efficient columnar storage format used in Hadoop ecosystem. It optimizes for read performance, compression, and improved efficiency in data processing. Data caching strategies. 1. In-memory caching, stores data in the RAM of a server for quick access. Examples include Redis and Memcached. Ideal for frequently accessed data. 2. Distributed caching, spreads data across multiple servers, reducing load on a single server and increasing scalability. Examples include Hazelcast and Apache Ignite. 3. Database caching, stores query results to speed up future queries. Can be implemented within the database or by using external tools. 4. Application level caching, involves caching data within the application layer. This can be specific to business logic, like caching user profiles or product information. 5. Content Delivery Network, CDN, caching, distributes and caches content geographically closer to users to reduce latency. Common in web services for static content caching. 6. Cache invalidation strategies, techniques to ensure cache consistency, like time to live, TTL, write through, write around, and write back caching. 7. Cache refresh strategies, methods to update cache, including lazy loading, on demand, and eager loading, preloading data into cache. Data privacy and anonymization. 1. Importance of anonymizing data. Anonymizing data protects individual privacy, complies with data protection regulations, like GDPR, and reduces the risk of data breaches. It involves altering personal data so that individuals cannot be easily identified, thus preserving privacy while maintaining data utility. 2. Data masking, a process of hiding original data with modified content, characters or other data. It is used to protect sensitive data while maintaining a functional substitute for testing or user training. For instance, replacing characters in a credit card number with X's except for the last 4 digits. 3. Tokenization, the process of replacing sensitive data with unique identification symbols, tokens, that retain all essential information about the data without compromising its security. Commonly used for protecting credit card data in online transactions. 4. Differential privacy, a system for publicly sharing information about a dataset by describing patterns of groups within the dataset while withholding information about individuals in the dataset. It adds noise to statistical data to prevent the identification of individuals, ensuring individual privacy. Benefits and challenges of data anonymization. 1. Protects user privacy. Anonymization techniques protect individuals' personal information from unauthorized access. 2. Complies with legal standards. Helps organizations comply with data protection laws like GDPR, HIPAA, which mandate protecting personal information. 3. Data utility. Anonymization allows the use of data for analysis and research while protecting privacy, maintaining a balance between data utility and confidentiality. 4. Risk of re-identification. Despite anonymization, there is a risk of re-identification if sufficient auxiliary information is available. Therefore, it's important to apply robust and comprehensive anonymization techniques. Different visualization techniques. 1. Bar charts, useful for comparing different groups or tracking changes over time. Ideal for discrete data categories. 2. Line graphs, best for displaying data trends over time. Useful in showing continuous data, such as stock market trends or temperature changes. 3. Pie charts, effective for showing parts of a whole. Used when the total of all segments equals 100%. 4. Scatter plots, ideal for showing the relationship between two variables. Useful in identifying types of correlation, or distribution trends. 5. Histograms, similar to bar charts but used for showing the distribution of a dataset. Good for understanding the frequency of certain ranges of values in a dataset. 6. Heat maps, visualize data through variations in coloring. Useful in representing the density of data, ranging from most intense to least. 7. Area charts, similar to line graphs but filled below the line. Useful for representing cumulative totals over time using numbers or percentages. 8. Bubble charts, a variation of scatter plots, where each point size is an additional dimension of the data. Useful for comparing and showing relationships between categorized circles. 9. Tree maps, ideal for displaying hierarchical data and part-to-whole relationships using nested rectangles. 10. Box plots, used to show the distribution of data based on a 5-number summary, minimum, first quartile, median, third quartile, and maximum. Choosing the right visualization technique. 1. Consider the data type. Different visualizations are suitable for different types of data, for example, continuous, categorical, hierarchical. 2. Understand the audience. Choose a visualization that resonates with your audience's level of expertise and familiarity with the data. 3. Define the purpose, whether it's to show a trend, make a comparison, or highlight a distribution. Your objective should guide the choice of visualization. 4. Keep it simple. The best visualizations are often the simplest. Avoid overcomplicating the graphic with too much information or complex designs. Data fabric versus data mesh. 1. Definition of data fabric. A data fabric is an architecture and set of data services that provide consistent capabilities across a choice of endpoints spanning hybrid multi-cloud environments. It's designed to offer a unified, integrated view of data across the organization. 2. Definition of data mesh. Data mesh is a decentralized approach to data architecture and organizational design. It treats data as a product, focusing on domain-oriented ownership, data as a product, self-serve data infrastructure, and federated computational governance. 3. Key focus areas. Data fabric focuses on integration and interoperability of data across various platforms. Data mesh emphasizes on organizational design and domain-oriented data ownership and architecture. 4. Implementation approach. Data fabric is implemented through technologies like data integration, APIs, and middleware. Data mesh relies on a shift in organizational structure, where cross-functional teams own and provide data as a product. 5. Technology stack. Data fabric leverages technologies like AI, machine learning, and advanced analytics. Data mesh uses technologies that enable domain-oriented data ownership, such as data catalogs and domain-specific pipelines. 6. Organizational impact. Data fabric affects the technological infrastructure of an organization, whereas data mesh impacts both the organizational structure and the approach to data management and operations. Benefits and challenges of data fabric and data mesh. 1. Benefits of data fabric: improved data accessibility, enhanced data governance, real-time data insights, and reduced data silos. 2. Challenges of data fabric: requires significant investment in integration technologies, potential complexity in implementation, and reliance on sophisticated AI and ML algorithms. 3. Benefits of data mesh: promotes a more agile and responsive data architecture, domain-specific data ownership, and enhances collaboration and autonomy among teams. 4. Challenges of data mesh: demands a significant shift in organizational culture, requires strong domain expertise, and can lead to challenges in maintaining consistency and governance across decentralized teams. SQL basics. 1. What is SQL? SQL, Structured Query Language, is a standard programming language specifically designed for managing and manipulating relational databases. It is used to query, insert, update, and modify data. 2. SQL syntax. SQL syntax includes various commands, clauses, and predicates. It follows a declarative pattern, allowing users to specify what data is needed, not how to retrieve it. 3. Data definition language, DDL, includes commands like create, alter, and drop. These commands are used to define and modify database schema and structure. 4. Data manipulation language, DML, consists of commands like select, insert, update, and delete. These are used for retrieving and modifying data within database tables. 5. Data control language, DCL, includes commands like grant and revoke, which are used to control access to data in the database. 6. Basic SQL commands. Select, used to select data from a database. Insert into, used to insert new data into a database. Update, used to modify existing data. Delete, used to delete data from a database. SQL query structure. 1. Select statement, specifies the columns to be displayed in the query's result set. 2. From clause, indicates the table from which to retrieve data. 3. Where clause, Used to filter records based on specified conditions. 4. Group by clause, groups rows that have the same values in specified columns into summary rows. 5. Order by clause, specifies the sorting order of the query results. 6. Join operations, used to combine rows from two or more tables based on a related column. Types include inner join, left join, right join, and full join. SQL join operations. 1. Inner join, returns records that have matching values in both tables. 2. Left join, or left outer join, returns all records from the left table and matched records from the right table, or null if there is no match. 3. Right join, or right outer join, returns all records from the right table and matched records from the left table, or null if there is no match. 4. Full join, or full outer join, returns all records when there is a match in either left or right table. 5. Cross join, returns the Cartesian product of two tables, all combinations of rows from both tables. 6. Self join, a regular join, but the table is joined with itself. Join examples. 1. Inner join. 2. Left join. 3. Right join. 4. Full join. 5. Cross join. 6. Self join. SQL functions and expressions. 1. Scalar functions, operate on an individual value and return a single value. Examples include upper, converts text to uppercase, lower, converts text to lowercase, and round, rounds a numerical value. 2. Aggregate functions, perform calculations on a set of values and return a single value. Common examples are sum, calculates the total sum, average, calculates average, count, counts the number of rows, min, finds the minimum value, and max, finds the maximum value. 3. Date and time functions, extract or manipulate date and time values. Examples include now, returns the current date and time, date_part, extracts a part of a date, and datediff, calculates the difference between two dates. 4. String functions, perform operations on string data. Examples include concat, concatenates two or more strings, length, returns the length of a string, and substring, extracts a substring from a string. 5. Mathematical functions, perform mathematical calculations. Examples include ABS, returns the absolute value, power, raises a number to the power of another number, and SQRT, calculates the square root. 6. Conditional expressions, used to perform operations based on conditions. The most common is the case expression, which acts like an if-then-else statement. 7. Case statement, allows for condition-based selection of data. This is used to implement conditional logic in SQL queries. Using SQL functions and expressions. 1. Enhancing data retrieval, functions and expressions can be used to refine and customize data retrieval, making it more relevant and specific. 2. Data aggregation and analysis, aggregate functions are critical for summarizing and analyzing data, especially in large datasets. 3. Data formatting and manipulation, string, date, and mathematical functions help in formatting and manipulating data to fit the requirements of your analysis or output format. 4. Complex query construction, using conditional expressions and case statements, complex queries can be constructed to handle multiple conditions and scenarios. 5. Efficiency and performance, proper use of functions and expressions can significantly improve the efficiency and performance of SQL queries, especially when dealing with large volumes of data. SQL aggregate functions. 1. Sum function, adds all the values in a specified column. Syntax, sum column _ name. Used to find the total of numerical columns. 2. Average function, calculates the average value of a specified column. Syntax, average column _ name. It excludes null values from the calculation. 3. Count function, returns the number of rows that matches a specified criterion. Syntax, count column _ name. It can also be used to count all rows in a table with count. 4. Min function, retrieves the smallest value in a specified column. Syntax, min column _ name. Useful for finding minimum values in a dataset. 5. Max function, retrieves the largest value in a specified column. Syntax, max column _ name. Useful for finding maximum values. 6. Group by clause, used with aggregate functions to group the result set by one or more columns. Syntax, group by column _ name. It's useful for summarizing data. 7. Having clause, used to filter groups based on a condition, particularly with the group by clause. Syntax, having condition. It's like where but for groups. Applying SQL aggregate functions. 1. Data summarization. Aggregate functions are essential for summarizing large datasets into meaningful insights, like total sales, average prices, etc. 2. Statistical analysis. These functions are pivotal in performing basic statistical analysis on data, such as finding averages, minimums, and maximums. 3. Data reporting. They play a critical role in generating reports, where summarizing data into aggregate figures like totals and averages is necessary. 4. Performance optimization. Using aggregate functions can greatly enhance query performance by reducing the amount of data processed and transferred. 5. Complex query building. They can be used to build more complex queries, especially when combined with the group by and having clauses, to extract specific insights from large datasets. SQL transactions. 1. Definition of a transaction. In SQL, a transaction is a sequence of one or more operations performed as a single logical unit of work. A transaction can involve multiple steps, but it either all succeeds or all fails. 2. Properties of transactions, ACID. Transactions in SQL are characterized by ACID properties, atomicity, all or nothing, consistency, ensuring data integrity, isolation, independence from other transactions, and durability, persistency of completed transactions. 3. Begin transaction, marks the starting point of an explicit transaction. It's used to start a new transaction block. 4. Commit, commits the current transaction, making all changes made during the transaction permanent. 5. Rollback, undoes all changes made in the current transaction. It's used to roll back a transaction if an error occurs or if the transaction needs to be aborted. 6. Save point, creates points within a transaction to which you can later roll back. This allows for partial rollbacks and more complex transaction control. 7. Transaction isolation levels, determine how transaction integrity is visible to other users and systems. Common levels include read uncommitted, read committed, repeatable read, and serializable. Managing SQL transactions. 1. Ensuring data integrity. Transactions help ensure data integrity by grouping related operations into a single unit that either succeeds or fails completely. 2. Handling database errors. Use rollback to revert changes in case of errors or issues, preserving the database's consistent state. 3. Maintaining database performance. Transactions can be optimized to minimize their impact on database performance, particularly in high-traffic environments. 4. Complex transaction management. SavePoint allows for sophisticated transaction management, enabling partial rollbacks and finer control. 5. Concurrent transactions handling. Proper transaction isolation levels help manage the visibility and effects of concurrent transactions, ensuring data consistency and preventing issues like dirty reads or phantom reads. SQL indexing. 1. Definition of indexing. In SQL, indexing is the process of creating an index, a data structure that improves the speed of data retrieval operations on a database table. Indexes are used to quickly locate data without having to search every row. 2. Types of indexes. Common types include primary indexes, unique indexes, and full text indexes. Primary indexes are automatically created for primary key columns, ensuring uniqueness. Unique indexes prevent duplicate values in a column. Full text indexes are used for efficient searching of text within columns. 3. Creating an index. Use the create index statement to create an index on a table. Syntax: create index _name on table _name, column 1, column 2, 4. Advantages of indexing: increases the speed of data retrieval operations, enhances performance of queries, and reduces the time taken for sorting and joining operations. 5. Disadvantages of indexing: can slow down data insertion, deletion, and update operations due to the need to maintain the index. Also, indexes consume additional storage space. 6. When to use indexing. Indexing is most beneficial on tables with large volumes of data and columns frequently used in where clauses, join conditions, or as sorting and grouping fields. Best practices in SQL indexing. 1. Index selection. Choose the right columns to index based on query patterns and column selectivity. Avoid over-indexing tables as it can degrade write performance. 2. Maintenance of indexes. Regularly maintain indexes to avoid fragmentation, which can degrade query performance. This can involve rebuilding or reorganizing indexes. 3. Balancing indexes. Find a balance between the number of indexes and the performance benefit they provide. More indexes can improve read performance but may degrade write performance. 4. Monitoring index performance. Continuously monitor the performance of queries and indexes. Remove indexes that are no longer used or that contribute little to performance improvement. 5. Considering data changes. Be mindful of how data insertions, updates, and deletions affect index performance and structure. Frequent changes can lead to index fragmentation. Thanks for watching.